Hello class, this is Mr. Lehman. Today we want to talk about two of our gas laws, Boyle's Law and Charles's Law. So let's start out with Boyle's Law. In Boyle's Law, the mathematical relationship between volume and pressure is studied, and the relationship has been found to be that there's an inverse relationship between the two. So as volume goes up, pressure goes down, and as volume goes down, pressure goes up as a result. So the question is why? So there's a good simulation out there that we may have used in class already, but we're going to check this out. So let's pump some air into a container, into our box. This could be a football, it could be a basketball, it could be a tire, it could be an aerosol can, but we're going to have a flexible container here, meaning that we can make it get bigger or smaller. So let's say it's something like, a syringe or a piston. Watch the pressure gauge as I do this. As I make the box smaller, as volume goes down, and let me try this one more time. Let me keep temperature constant. Pump some air in. So if temperature is constant, the temperature will change, but the simulation tries to cool it back down as it heats up. So as we make the volume smaller, watch the pressure gauge. The particles are going to collide more often because they have less space to move around. They're closer together. And the smaller the space, the smaller the volume, the more the collisions, the greater the pressure will be. Alright, so as volume goes down, there's more collisions. As a result, pressure goes up. Now if we back it out the other way, if we make our container bigger, watch the pressure gauge. As volume goes down, the particles have more room to move around, and they're going to collide less often, creating less pressure. So that is Boyle's Law. Alright, we look at a graph, inverse relationship. As one goes up, the other goes down. Alright, so an inverse relationship, we get a downward sloping curve like you see here. And a saying to help you remember Boyle's Law: Boyle is a VIP. Yes, he's a very important person, or was a very important person, but what this stands for is volume inversely related to pressure. Alright, if we look at a low pressure, high pressure environment, once again, the more room the particles have to move around. If we keep temperature constant, the less often they're going to collide. The smaller, the lower the pressure will be. If we push down on our cylinder, on our piston, force the particles into a smaller volume, they'll collide more often, and we get a greater pressure. And we see that on the pressure gauge. Something we did in class maybe already is a marshmallow demo. We put a marshmallow inside of a syringe. Alright, and we push down on the plunger. As we push down on the plunger, we're forcing the air particles that are inside here, moving around, colliding, pushing in on the marshmallow. We force them into a tinier volume, and so those particles will crash into the marshmallow more often, creating more pressure and making our marshmallow get smaller. So that marshmallow allows us to visually see the increase in pressure. Mathematical formula: V1 times P1, initial volume times the initial pressure, is equal to the final volume times the final pressure. Just something to look out for here is we want to make sure that the volumes are in the same units. So if you start out with liters and it gives you a volume in milliliters, like we can't use both these two different systems of pressure. We have to convert either milliliters into liters or liters into milliliters. Just remember, 1 liter is equal to 1,000 milliliters. Pressures, we talked about different systems of pressure already. You can't use two different systems of pressure. So if you're given like ATMs of pressure, you can't use like torr of pressure over here. So conversion factors for pressure, just a quick refresher. We like to use atmospheres as much as possible. So that's what we're going to use for the ideal gas law. 1 atmosphere of pressure is equal to 760 torr. We'll push a mercury barometer column up to a height of 760 millimeters of mercury, is equivalent to 14.7 pounds per square inch of pressure, and is equal to 101.3 kPa, kilopascals of pressure. So you use these for your conversions. So if we look at a simple example of this, let's say we're at sea level. At sea level, standard pressure is just 1 atmosphere. So let's say we have a balloon. The balloon is 15 liters in size. We're at sea level, pressure is 1 atmosphere. Let's say that we take our balloon, we immediately start to hike up a local mountain next to the beach. On top of that mountain, the pressure is only 0.7 atmospheres. The question is, what will the final volume of that balloon be? Well, if we think about it, so our pressure is going down, so as a result, volume has to be getting bigger, so it needs to be a number bigger than 15. So 15 times 1 is 15. 15 is equal to 0.7 times V2. So we divide both sides by 0.7, and 15 divided by 0.7, we're looking at about 21.4 liters. Since our original volume was in liters, the final volume will be in liters. And I didn't worry about sig figs right here, so I tend to be a little bit more relaxed about sig figs when doing these types of problems because we're dealing with temperature and pressure conversions. Alright, so that is Boyle's law. Volume is inversely related to pressure. Charles's law, another gas law, there's a direct relationship between temperature and volume. One thing I want to point out is we have to use the Kelvin temperature scale. We can't use Celsius or Fahrenheit. So you always have to use Kelvin. As Kelvin, absolute 0 is 0 Kelvin. All the temperatures are positive. That's pretty much gives you the absolute, the true temperature, the true relationship of energy that those particles have. Remember, temperature is equal to the average kinetic energy of particles. So if we go back to our simulation, and now if we heat up, we try to keep temperature the same. If we change volume, watch as let's do this. If I heat this up, if I heat it up, if this represents the balloon's going to get bigger. Why? Because the particles are moving around faster. So the faster the particles move, the more they're going to collide, the more force at which they're going to collide as well. And so the object will be able to expand and get bigger if it's a flexible container like a balloon. If I cool down a gas, if I say I stick a balloon in a freezer, then slowly over time, as the gas particles cool down, they're going to move slower. If they move slower, they're going to collide with less force, create less pressure, and so the outside air pressure will push in and compress the gas. So as temperature goes up, particles move faster. Our objects can expand if they're in a flexible container. As temperature goes down, particles move slower, they collide with less force, and they will contract or compress. Alright, so that is Charles's law. Alright, let's take a look at a little bit more here. Graphing-wise, direct relationship. So if we double the Kelvin temperature, volume will double. If we triple the Kelvin temperature, volume will get 3 times bigger. Quadruple the Kelvin temperature, volume will get 4 times bigger. The formula V1 over T1 is equal to V2 over T2. Notice because it's a direct relationship and not an inverse, volume's on top, temperature's on the bottom. We have to use Kelvin for temperatures. To go from Celsius to Kelvin, we add 273 degrees to the Celsius temperature. So simple application of this, let's say our original volume is 15 liters. We're taking our balloon. Our balloon, let's say, is at a temperature slightly above room temperature, 300 Kelvin, which is 27 Celsius, which is probably about 80 degrees. If we take that and we stick that balloon in the freezer, if it goes down to the freezing point of water, 0 Celsius, 273 Kelvin, 32 Fahrenheit, how big will the balloon be? So what is our final volume? When we got this set up like this, we're going to multiply, cross-multiply, and solve. So we're going to take 15, what's on top on the left side, multiply it by what's on the bottom of the other side. That gives you 4,095, and we'll divide that by 300, and that gives us volume is 13 point roughly 7. So volume is about 13.7 liters. And once again, I didn't worry about sig figs. And so think about your answer. Temperature's decreasing, so volume would have to decrease because of that direct relationship. Alright, so that's our first 2 gas laws. Hopefully that helps. Have a great day.